Good afternoon, everybody. Welcome back. Okay, a couple of housekeeping announcements. I sent out a message on Canvas a little while ago, reminding everybody of what's going on. So tomorrow we do have a lab, and then next week we will have our first exam. So we will meet in here on Tuesday, 3 p.m. That'll be exam 1. It'll cover everything we've learned so far. It's all multiple choice. Need a Scantron form 882E. That's the strip that's got 50 on each, 50 multiple choice bubbles on each side. I will provide scratch paper, and there will be a formula sheet on the back if you are worried about it. And then I typically have allowed students to bring their own formula sheets in case they, if that makes you feel safer. But I will provide basically all the formulas that we need for the exam. Tomorrow's lab is going to be a direct application of what we learned today, okay? So if you are wanting a hint of what we're gonna do tomorrow, then my advice would just be pay reasonably close attention. Okay. Sweet. All the homeworks are going to be due next. Next Tuesday as well. That's not a deadline that I'm willing to compromise on. So if you need an extension, my response will almost certainly be 1 raised eyebrow plus a you had a month to figure this out. So that's my lone dad moment that I will dole out to all of you. Okay. Okay. Let's get things started. I have a short series of warm-up exercises for us to do. I don't know if anybody knows what these are, but these are referred to as crane scales. And I'm going to use a couple of these as a demo. So as my warm-up exercise, I'm going to draw a picture of kind of what I'm thinking. So this is a ceiling. Okay. I'm going to have exactly 1 kilogram hanging from a single string, okay, from a single string, okay. I feel like this isn't going to take 5 minutes, but I'm going to give us 5 minutes to just draw a force diagram. Just draw your free body diagram of exactly this setup, and then we will go from there. All right, folks, I feel like we didn't need that long, but how are we doing on a free body diagram of a single weight hanging from a single string? Do we need more time? Or is it time to boogie? All right, boogie time. Okay, my big question to you is if I have 1 kilogram hanging from a string, is it moving at all? If it's just suspended there, it's not bouncing up and down, it's not swinging left or right. If it is just hanging in place, is it moving? Not a trick question, okay. If it's not moving, is it accelerating?
No.
Right, the speed is not changing. So if the speed's not changing, the velocity's not changing, then it's not accelerating, okay? So quick question, okay, if something is hanging by a single string, do I have any forces that are pointing left or right?
No.
Not that I can think of, right? So the only forces that I have to think about are going up and down, right? Okay, so what are my forces that are going up and down in this case?
Gravity.
Gravity, you guys are pros, okay? If we forgot about gravity, I was gonna have to do some serious soul searching on my own. Okay, so I've got my weight, okay, that's going down. But we agreed that it's not accelerating, so there's gotta be something that's pushing it back up. What's that force?
Tension.
You guys are pros, sweet. So the force that is pushing it back up, I'm just gonna put a little arrow over that and call it tension, okay? And then, is there anything else? Not a trick, right? Okay, sweet. So here is my demo. I've got, it's a little bit more than a kilogram here, just because just the weight, let's see. Okay, so I've got a crane scale. Okay, right now it should be zeroed out, I'm hoping. Okay, sweet. Okay, and then it's reading in newtons right now because we are, after all, talking about forces. So I'm expecting this to be, please don't fall. Yay, sweet, 9.8 newtons. There we go, yay. Okay, so this is effectively what I've drawn here, okay? Newton's second law told us that if I know all the forces that are acting on an object, and if I sum them together, I know that object's mass times its acceleration, okay? Just to reiterate how important this is, not just to this class, but to Physics 4B, to some extent Physics 4C, and the rest of your engineering careers. This is something that, not that I would ever do this, but this is an equation I would get tattooed on me, 100%, okay? You can literally do the rest of Physics 4A with just that equation. That is a Mr. S guarantee, okay? If I add all my forces together, okay, and we agreed that aside from my inability to keep that still, okay, it's effectively not moving, right? If it's not moving, that means it's not accelerating. We can agree on that? Yes? Okay. So when I add all my forces together in this case, and if it's not accelerating, what should that add up to? If it's not accelerating, what should my sum of all my forces add up to in this case?
0.
Should add up to 0, right? Sweet. So this is my first example. Okay, this is how we do Newton's laws. Okay. First, I would always recommend drawing a picture because that will help you do things. Okay. So in this case, I'm going to, and remember, force is a vector. So at some point we might need to break things up into components. Okay, keep that in mind. Okay, so first things first, I only have to worry about the y direction in this case. So I'm gonna call, that's gonna be positive y. Okay, if I sum up all the forces in my y direction, let's see, so this is how I'm gonna write this out. The sum of all my forces in the y direction, tension is pointing up, yes? Okay, so it'll be tension, and then the weight is going down, yes?
Yes.
So that would be minus mg. And then once I've effectively done all my forces in the y direction, this is when I write equals, I would write ma, right? But we all agreed that it's not accelerating if it's not moving, right? So that's the point where I write 0, okay? And just as a precautionary note, this is going to be, that would be MAY, okay? Just to be clear. So the reason why we said that that's 0 is because it's not moving, okay? Cool. Okay, how do we feel about this first example? On a scale of 1 to 5, 5 being impossible, 1 being super easy, how do we feel about this first one? Okay, sweet. Let's make this more complicated, because we can always make things more complicated. Okay, I'm going to turn you off momentarily. No, off. Okay, I want to do, can you chill, dude? I didn't have very much time to figure out how to work these. Okay, sweet. Okay, what if I had 2 strings? Okay, this is going to be more of a thought experiment than anything else. Okay, let's say I'm going to get rid of all of the weight first. Okay, so let's say I had 2 of these bad boys, and I had the weight distributed out over both of these. In my drawing of this, I'm going to have them be the same length. As a professional, I'm just going to tell you that the length doesn't matter. Okay, so let's do a force diagram of this setup. I'm eventually going to have 1 kilogram on here, and then I'm going to ask you guys a conceptual question over here. So I'll give you guys a couple minutes. So this is my force diagram. Okay. Okay, that's still 1 kg. Okay, nothing new here. But now I've got two. Okay, now I've got 2 strings holding it up. And I don't think so. I'll give you guys 2 minutes because I don't think the drawing is going to take very long. But go ahead and draw a force diagram of those 2 things, and then we'll go from there. And then I'll explain myself. Explain yourself. Thank you. Okay, how do we feel about the drawing? Okay, let's figure this out. So, what are all the forces that are acting on my 1 kilogram weight here?
Gravity and tension.
Gravity and tension. Anybody have any disagreements with that? Gravity and tension. Okay, so gravity is always going to go down, straight down. Nothing changed there. Okay, but now, what do my tensions look like? There go. Excuse me. Now I have 2 tensions to worry about. Okay, sweet. So I have a tension going that way, and I have a tension going this way. Okay, sweet. I'm gonna call that T1 and T2. Okay, my intent was for these to be the same angle. I suspect that I didn't do that very well, but let's figure that out. Okay, so I have 2 things that are going at an angle. So here is my next question to all of you. Okay, I'm going to give you guys a couple minutes to discuss with the people at your table, okay? The magnitude of the tension, okay? Do we think, because now I've effectively split the weight between two different strings, right? Okay, so here is my conceptual question to you. Is the sum of the magnitudes, so actually I'm just going to write this out. Okay, are the sum of my magnitudes T1 plus T2, is that going to be option A? Is it going to be greater than mg? Is it going to be less than mg? Or will the sum of the tensions equal mg? I'm going to give you guys 2 minutes to discuss that with the people at your table. What do you guys think?
Well, it's equal, but in the opposite direction.
Yeah.
Or sorry. But the
Yeah.
same number.
Yeah. Yeah, technically.
So, yeah, think of, like the strings as magnitude. So, the two tension added up cancels out the,
I still think
these are tension to the mg is negative.
Yeah.
But there's the x y as well. So I think that
well, absolute value.
is that that's the number of tensions.
Yeah.
They were fun to me.
Yeah. No, you're right.
Okay, let's go. We'll go through the calculation. I'm not gonna spare. We'll go through it. Okay, so do we have to worry about horizontal components right now?
No.
We don't?
Oh, sorry. Not
Yes,
you do.
we absolutely do now. Now we have things we have tensions that are going at angles. Okay, so, but the good news is in this example, is anything moving? No, okay. And again, my aim was for these to be at the same angle, so I'm gonna say that these are the same angle, okay. The setup probably didn't happen that way, but let's figure this out, shall we? Okay. So I want to break things up into the x components and y components. In my head, I just think x going first makes more sense, but in reality, it doesn't matter. So let's sum up all the forces that are in the x direction, okay? Let's do this, okay? So this is how, when I went to physics school, this is how I learned to do this, okay? So the sum of all the forces in the x direction. Okay, so I'm still going to say that that's positive y, and I'm still going to say that's positive x. Okay, later today we'll see why that might change. Okay. Okay, so where do you guys want to start? Okay, any ideas? Nothing. What is going in the x direction now? That.
Chin.
Yes. Okay. Tension. Yes. Okay. How do I find the x component of my tensions, though? I know the angle. I'll say that I know the angle. this might be a nice, good beginning to reviewing stuff for our exam, okay? So if I know my angle, okay, and then this is the arrow it's pointing in, okay? How do I find the x component of my tension? Yeah, let's use cosine. Okay, so I'm gonna say that the angles are the same, so I'm gonna say T1 cosine theta, okay? That's pointing this way. Okay, T2, is it gonna be a plus or a minus now? It's gonna be negative, right? I'm gonna say minus T2 cosine theta, okay? Is there anything else pointing in this way direction? It was just those two tensions, right? Okay, sweet. So that's the point where I'm gonna say equals 0. Okay, there's no accelerations in the x direction. Okay, let's do it in the y direction. I bet you guys know what to do. So this is, when I went to physics school, I just said, write down the sum of all the forces in the y direction. Okay, you guys tell me, now what's going on in the y direction here? T1 sine theta, they're both pointing up, right? T1 sine theta, that would be T1y, this would be T1x, okay? And then T2 sine theta, that would be this part, that's pointing up, okay? What's the part that's going down though? Gravity. It's the most depressing force in the world because it always brings you down. Minus mg, and that equals 0, right? Because it's not moving up or down.
So
yes?
Are we saying gravity is positive 9.8 then because we're doing the minus part?
That's fair. Yeah, I'm going to just say that that's minus g. Yeah. Cool. Okay. All right. So let's figure this out, okay? I wanted to sum together the magnitudes, okay? I wanted to figure this out, okay? Where do I go from here, okay? Well, first things first, okay, if I know my angles are the exact same, it's not always gonna be the case. If I know my angles are the same, here's how I'm gonna do this, okay? That was a good setup color. I think purple's a good solution color. I know that these two add up to 0, so I'm going to say T1 cosine theta, and that equals T2 cosine theta. Okay. If the angles are the same, what does this statement effectively mean? Yeah, exactly. They both have the same factor. That means the magnitude of T1 is equal to the magnitude of T2. Okay. Means those magnitudes are the same. Okay, sweet. How's this looking over here? Does this mean that they're going to split up evenly, or I don't know? We'll find out. Okay. I'm just going to make my life easier and then drop the subscripts. Since the magnitudes are the same, I'm just going to call them t. Okay. So let's find out what this means. Okay. I'm going to substitute this information. Okay. I'm just basically going to drop the subscripts here. And here's what this looks like to me. I'm going to say t sine theta plus another t sine theta, and that's going to be minus mg equals 0. Okay, I basically just substituted that information around, right? Okay, but these two are the exact same thing, so here's what that means. So 2 times t times sine theta equals, oh, I'm cutting to the chase here. T, that equals 0. Okay, so far so good. And then my goal was to basically figure out what t is. That's basically what I'm looking for. Okay, and in fact, I've kind of done that over here. Okay, the 2t, that's the sum of my 2. Okay, let's keep going here. I'm going to solve for 2t. So I'm going to go 2t is equal to mg divided by sine of theta. Okay, now it depends on what my angle is. Okay, I did not get a protractor out to measure this, but ooh, My phone's in use, otherwise I'd use it. Okay, but let's figure this out. Okay, so my question to you is, for any angle between 0 and 90 degrees, okay, which I'm going to say, I feel pretty safe in saying that. So theta is between 0 and 90 degrees, okay. Does that mean sine of theta is greater than, or 1, less than 1, or equal to 1? If it's between 0, if theta is between 0 and 90 degrees.
It's between 0 and 1.
It's between 0, all right, it's between 0 and 1, right? So theta, that means sine of theta is less than 1. Would you guys, right, would you guys feel safe if I said that? Okay, so what does that mean? The sum of my two tensions has to be greater than. Oh, actually, I kind of gave it away, okay? So here's a better question. The sum of my two tensions, that's what this was. This is T1 plus T2. Okay, so T1 plus T2. Does that mean it is greater than the weight? Is it going to be less than the weight, or is it going to be equal to the weight?
Greater.
It's greater than. Okay, let's see if that holds up. Okay, so this is supposed to be 1 kilogram, so I'm expecting that if it's going to be greater, oh, I should turn these on first. Let's do that. Let's see how it goes. Okay, the magnitude of my two tensions should be greater than 9.8 newtons. Okay, and I'm going to work my way this way. I would laugh really hard if this just ripped everything off the wall. Okay, so I've got 6.9 over here, and I've got 5.9 over here. Okay, so in this case, T2 was 6.9 newtons, T1 was 5.9. When I add those two together, is that greater than, or is that less than or equal to 9.8?
Greater.
It's greater than. Sweet. So that checked out. Okay. What happens if I make my angle? What happens if I make my angle more narrow? Okay. Does that mean it's the sum of those two is going to decrease, or is it going to increase? You guys tell me.
Decrease.
It's going to decrease. Let's see if that holds up. Okay. Oh no! Oh no! The friction on the board. Okay. Okay. So it did drop. Okay. I'm gonna raise you. Okay, sweet. Oh, that's not gonna work. Darn. All right. Well, I have to hold things in place. That's kind of lame. But oh well. So I have 3.9, and that didn't change. That's still 5.9. Did that go up or down? The sum of the two tensions. It went down. Okay, sweet. What happens? Okay, I don't think this is physically realizable, but oh yeah, I'm really ruining it here. Okay. When those two are both equal to 90 degrees, okay, then what happens? Yep. Then I've divided the force equally between these two strings, okay? The sum of the sine of 90 degrees, that's 1, right? And then, so when theta was equal to 90 degrees, then the tension in one string, in this case, is going to be equal to mg divided by 2. Sweet. And then we've split it up, okay? The whole point of this exercise was to show you that force adds like vectors, okay? That was my proof of concept, okay? I know that was a lot of parts moving around, but are there any questions on how this kind of thing works? Okay. Let's do another example, shall we? Actually, before I move on, okay, I'm gonna take that off. Okay, I need my board space back. Thank you to the people that are kind enough to lend me toys so I can do things in my physics class. Okay, before we move on, when we were making our force menu last week, I neglected quite possibly like the most important force that we might need in this class. Okay, if you saw me writing on the board and you saw something that didn't look recognizable, that's because I forgot to tell you about it. The one other force that I forgot to talk about was the spring force. Okay. We have all encountered springs of some kind in our lives, yes? Have we all encountered a rubber band in our lives? Okay, we've all encountered rubber bands in our lives. I don't know about you guys. I had the can't really call them friends, but I had friends in middle school and high school that would take rubber bands and they'd leave a nice little welt on me to go home with. Okay, so the more you pull back on it, here's the idea of the spring force. Okay, a drawing of a spring that you'll see either in your textbook or on an exam or something. Typically, a spring is just going to look like a zigzag line like that. Okay, this is supposed to be my drawing of a spring. Okay. Here is how would you guys agree with me if I said that when I pull, like the more I stretch a spring, the more it kind of pulls back on you? Is that fair to say? Does that corroborate with their everyday experiences of springs or elastic things? The more you pull on it, the more force you have to pull on it to extend it farther and farther. Yeah? So here's the idea. I'm just going to say that I have a spring attached to a box. This is not the most relatable experience of all time, okay? I'm going to call that x equals 0, okay? So right now, if I were to just let this go, nothing would move, okay? But let's say that I extend it. So I'm going to say that that's where my equilibrium point was. Okay. Okay, and then that's my new point. Okay. Okay, I have extended it, okay, by x minus x naught. Okay, I'm going to call that's going to be my change in displacement here. Okay, since I have pulled it this way, the force from the spring acting on my object, which way does that point? Which way do you feel the spring pulling? Do you feel it pulling this way with you, or do you feel it opposing you? It's opposing me, right? Okay, if you get bored and you're at home, that would be the force of my spring. Okay, and the more I stretch it, experimentally, what we found with most springs, or most elastic objects, at the very end of the semester, we'll see kind of where this comes from. So if you have more questions about this, then hang tight. Okay, what we tend to see is that the force per unit length extended tends to increase linearly, okay, up to a point. Okay, I have a nice long presentation about this at the end of the semester. Okay, the moral of the story being that the force from a spring increases with, I should say the magnitude of the force increases, okay, with the displacement. That's the moral of the story here. Okay, and then the way I can finally, once and for all, and since experimentally, or at least experientially, when we play with springs and when we pull on them, we feel the force of the spring pulling back on us, so it's pointing in the opposite direction. Okay, the force of a spring, therefore, is minus, that's telling me it opposes me. Okay, this K, that is called your spring constant. Okay, and then it's times its displacement. The key point being here is that, I wrote this over here, okay? The key point here is that it's its displacement from equilibrium, okay? That is the key point to take home. Okay, it's not its displacement from the origin, although very often the equilibrium point will be its origin, but there is maybe quite possibly an exam problem that I thought of that might make you think about that. Okay, things to think about. Okay, so that was my thing that I forgot. That's my bad. Are there any questions about kind of where we get the spring force and how I arrived there? Or are we in the mode of just like Mr. S, just moving along? Yeah, that's how we're feeling about this. Okay. here's my next example. Okay, this is gonna hurt our head. Okay, I need, if you have it with you, it might be useful to if you have it with you, your math preview, that was our first lab that we did the day after our first lecture meeting. If you have that with you, that might be useful to have on hand. But here is my next scenario. I moved last semester, so this is something that is just on my mind. Okay. I literally had to move a couch up an incline. Okay. Okay. So I did not drag it, fortunately, but let's just pretend like I'm not smart enough to do that. Okay. Okay. I'm gonna say that that's some angle. We'll get there. Okay. This is my couch. Okay. Because I'm gonna say it's moving at a constant speed. Okay, so v is a constant. Okay, so if the velocity is constant, what does that mean about our acceleration? Zero. Okay, sweet. Okay, sweet. Good to know. I'm going to say that I am pushing. I'm going to say that I'm pushing. I'm just going to call that F. Okay, I know that that's kind of confusing. Okay, I'm going to call that F. I'm going to call that FMS for Mr. S pushing a couch up a hill by himself. Okay. The next thing that I want us to do is we're going to draw a force diagram of this. Okay. So I will give you 2 minutes. Oh, and I'm going to say, up note, there absolutely is friction. Okay, there's friction. Okay. So I'm going to give you guys 2 minutes to draw the force diagram. Okay, the free body diagram. We'll go through the free body diagram. 3, 2, 1, force diagram. Feel free to also talk amongst each other. This isn't an exam. Okay, sweet. Let's do the free body diagram. Okay. I'm gonna drop this for a minute. Okay, sweet. I'm gonna pretend like that is where everything is directed. Okay. So what are all of the forces that are acting on my couch? Gravity. Okay, sweet. That's always a great starting point. Okay, I'm gonna get rid of that. I should have put that on top. Okay, gravity is always going straight down. Okay, that's the mass of my couch times gravity. Okay, what else?
Normal force.
Normal force. Okay, which way is the normal force pointing?
Opposite.
Opposite of? Okay,
Ground.
opposite the ground. Okay, I like that. The word that I like to use for that is perpendicular. Okay, it's perpendicular to the surface. Okay, so here is an example of a normal force that does not make sense. That is not the normal force. Bad. Okay, the normal force by definition is always going to be perpendicular to the surface in question. Okay. I shouldn't have even drawn that. I felt like that was actually more confusing. Okay, so the normal force, okay. Okay, what else? I already kind of drew one. That's me pushing it up the hill. I'm gonna move that around. It doesn't matter where it is. Okay, there's that. That's the force of Mr. S. Pushing the cart up the hill or pulling it, doesn't matter. Okay, what else?
Friction.
Friction, and which way is that going?
Opposite of the way you're pulling.
It's going the opposite direction of motion, okay? I like to use a curly F for that one, okay? Is there anything else? Not that I can think of. Can you guys think of anything else?
So are you pulling it or pushing it?
In this example, it doesn't matter.
Oh.
Yeah.
Because if you were pulling it, you would have a tension, right? Somewhere.
Yeah, in my arms.
Yeah.
Yeah, if I were going like this, yeah. As a matter of fact, that that is an example that I did want to do either if we have time at the end, or we'll do that first thing on Wednesday. Okay. I'm gonna say that my couch. I feel like this is overkill. I'm gonna say my couch is 50. Let's say my couch is it's about the mass of another human being, 75 kilograms. Okay. I'm gonna say that my driveway. I should measure this. I think my driveway is around 25 degrees at an incline. Okay. And then I want to say that my the coefficient. Okay, I did briefly mention this on Wednesday before we left. Is this going to be coefficient of kinetic friction, or is this going to be the coefficient of static friction?
Kinetic.
I heard different answers. Which one is it? Is my couch moving?
Yes.
Okay, that answers the question. Okay, this is going to be kinetic friction. Okay. I'm going to say that it's pretty hard to move it up. I'm going to call that 2. Okay. Okay. This is the hard part, and this is the part that's going to make our lives miserable. Okay. But I promise you, this is about as complicated as it gets. Okay. And this is only for one object. Okay. Once we get 2 things involved, then we have all sorts of shades of difficulty. Let's see. I've used green. I've used red. I haven't used blue yet. Let me dig around for a blue. Okay. How do I break this up? What do I do? Okay. I'm gonna kind of hold our hand through this one. Okay. This is why it's important, because over here I kind of defined what positive and negative was. I'm just gonna tell you that you can do whatever you want. Okay. You can do whatever you want. You're all adults. I would always make my x and y align up with the direction of motion. So here's what I mean. Okay, so I'm gonna call parallel to my driveway. I'm gonna call parallel to my driveway x, positive x, and then I'm gonna call perpendicular to my driveway y. Okay. I challenge you in your free time that I know none of you have because you guys are all busy full-time college students. Okay, I challenge you to go through all of this like this when you're bored. Okay, if you're ever bored on a rainy day and you're like, man, I sure miss Mr. S's Physics 4A class, I dare you to go through it like that and then tell me how much more frustrating it is. Okay, but here's why this is, the only reason why this is complicated is just because you have to tilt your head. Okay, so let's break this up. Okay, in my x direction, what are the forces that I have to deal with going up and down my driveway? So this would be this way. What are the forces I have to deal with in that direction? This would be me summing things up in the x and y direction. So the sum of my forces in this x direction. What do I got? Yeah, I got friction, okay? That in this case is going to be opposing me, yeah? So I'm going to say that that's a minus fancy F.
Gravity.
Gravity, yes, gravity is, okay. How much of it is opposing me? A little, a lot, some? Okay, this is the part where I was kind of this is why this was on your math preview. That was my best. Okay, I have a component of gravity. I have a component of gravity opposing me in this direction. Okay, this is the torture part. Okay, so I'm going to call that minus. I'm going to call that mgx. That's an x component. Okay, we'll get to how we figure out which one we're using. Anything else?
We're going to use Newton's second law
Yes.
for the gravity and normal force.
This is just this way.
Okay.
Yeah. We'll get to the y direction in a second. It's actually a little bit easier. Anything else? Yeah, it's me, my force. Yeah, I'm just gonna call that plus F. I forgot to specify that. I'm gonna say I'm insanely strong. I'm gonna say that FMS is 100 newtons. Okay. Okay. Actually, no. My goal is to figure out how hard I have to push this. I'm not even gonna specify that. Okay. I know everything else. Okay, and then I said that this was going at a constant velocity, so when I sum up all of my, what is my acceleration in this case?
0.
Sweet, 0. And just as a reminder, that's m a x. Okay. Cool. All right, I'm gonna leave a little space over here, and then we'll do the y direction.
Would it not be accelerating downhill?
I'm pushing it up my driveway at a constant speed.
Oh.
Yeah. So there's no acceleration. If the
Oh,
speed is
because we
constant,
already-
there's no acceleration.
Yeah, because we already put mg.
Yes. Yeah. Okay, we'll get to how we show that in just a second. Okay. Let's do the y direction. This is gonna be a little bit easier. Okay. This is how I did this in physics school, where I say, okay, the sum of all the forces in the y direction. The y direction is going this way. So what's going on in the y direction? Normal and gravity. Okay. So I've got my normal force, okay, pointing up. And then I've got gravity, but is it all of gravity?
No.
Not in this case. Nope. Okay, and it's going to be minus mg y. And this is the tricky part. This is going to hurt your head. Is it moving up and down in this case?
Yes.
Is it?
No.
I said that this is my y direction. So is it moving this way at all? No, it's not. Okay, this is the part that hurts my head. Okay, if I said, and even if I said that, it's moving at a constant velocity. So that means that both my x and y components are going to be constants too. So in both cases, equals 0. Okay, that's it. Okay. My question at the end of the day was, how hard do I have to push? So that's what I'm trying to deal with here. Okay. But I need to get it in these terms here. I need to get it in terms of the friction, I need to get it in terms of the angle, and I need to get it in terms of the mass of my couch. Okay. So where do I even go from here? I have a lovely, say again? Oh, sorry. I have a lovely list of forces that might help me out here. Here's a better question though. I said that I need to figure out what my x and y components of G are. Let's figure that out first, okay? Do we remember from our math preview? I know this angle. I know the incline of my driveway, yes? Okay. What is this angle here? Question mark. What is that angle? Say again? 90 minus the incline. That would be this angle here. Okay, that's that angle. Okay, so if this is, let's see, if this is a right angle, that means that's a right angle. Okay, this in here is 90 minus theta. Okay, do these two not have to add up to 90 degrees? Okay, this part, I should do this part, and then this part. Those have to add up to 90 degrees, do they not?
So it's the
What's theta?
It's just theta. Okay, that's why we did that in our math preview. Okay, so here's the tricky part. Okay, is my x component, is this going to be opposite of theta? Is it going to be adjacent to theta? It is opposite, so which trig function do I use now?
Sine.
I use sine for x? You guys didn't sign me up for this. Okay, so we're making progress here. So that's minus, I'm just gonna put all my positive stuff first. Okay, and then I'm gonna do minus, let's see, minus mg, okay, that is sine theta. Okay, and then that's minus friction. Okay, and that equals 0. Okay, anything else? Anything else I can draw from over here? Here's another part. Okay, I know that the friction is equal to the coefficient of friction, which I've specified, times my normal force. So I'm going to substitute that in here. That's okay. So that's my force that I'm supplying from pushing. Okay, minus mg times sine of theta, and then that's going to be minus mu times n equals 0. Okay.
And we can find the normal force.
We can find the normal force. How do we do that?
It's just opposite of our gravity and the below the one.
Bingo. I know everything. I know everything. Okay. All I need to do is just solve for n over here. So n was equal to mgy. Okay, so if I used sine for my x component, what does that leave me for my y component now? The part that's going this way. My angle is defined right in here, so that means my y component uses cosine now. That's the adjacent leg now. So my normal was mg cosine theta. Okay, this is why this is kind of important for us to have a understand what our definitions of our trig functions mean. Okay, it depends on where our angle is defined. Okay, I think I know everything now, right? Well, I was born feeling like I knew everything. Okay, I'm sure you guys feel the same way. Okay, I know my normal force. Okay, I know what mg and theta are. Okay, I know my coefficient of friction, and this is what I was looking for. Okay, I want to know how much force I have to supply. So let's figure this out. Okay, here we go. So I've got whatever my force is for Mr. S minus mg sine theta, and then I'm going to do minus This deserves another color. Okay, that goes. Oh, that should actually point. Hold up. That should go right there. Okay. Okay. And then I need mu times mg cosine theta, and then all of that equals 0. Cool. And we're basically done. Okay. Because all I need to do is just add all that stuff over to the other side, right? Yes. Cool. So in the end, the question that I was asking was how much force do I need to apply to move this up the hill? I'm going to do myself a solid and just factor out the mg that's here, just to make this prettier in my head. That'll be sine theta. I added this over, so this will be plus mu times cosine theta. Okay, let's see how much force I have to apply in this case. I think my couch in reality is more kilograms than that. So I get 9.8 times 75 times, let's see here, I got sine of 25 degrees, excuse me, plus 2 times cosine of 25 degrees.
For G, do we use positive or negative?
Use positive,
Okay.
yeah, because my force is being applied up that way, yeah. Oh my lord. Okay, at the end of the day, Mr. S has to go to the gym. That's going to be 1,600 newtons. Okay, that is in that ballpark. Okay, that's a lot. That's a lot of force. Okay, so the warning that I gave everybody last week was, remember how I said that this is like a nightmare because we have the versions of force that we need. Okay, the nightmare is going through all of this to move everything around. That was the nightmare. Okay, do we see where I'm coming from now? I see the look of hopelessness in all of your faces, and I'm just going to tell you it's okay. It's going to be okay. This is almost as bad as it gets. Okay. Okay. Are there any questions on this?
I'm just still a little confused on
Sure.
why why y isn't going upwards with the couch for x, y, x. I'm still trying
So, let me see. The question, let me see if I can paraphrase your question. Your question is, why did I not do this is y and that is x?
No.
Oh.
Why, if the couch is going upwards, y is not changing y?
Why is that not changing? So, I think the most convenient way, at the expense of having to think a little harder, the most convenient way to solve this problem was to say that this was perpendicular to my driveway, okay, not perpendicular to the sidewalk in front of my driveway. Perpendicular to my driveway is y, okay. I also said that I'm moving up my driveway. That is, I'm moving parallel to my driveway at a constant speed, okay. And according to just the way that I have chosen to define my axes, okay, the way that I've chosen to define that, I don't have a component of velocity in the y direction. There's no component of it going that way.
Oh, because it's only moving on the x.
Yes, okay. However, your question is not dumb, because if you did define it this way, then I would have a component of velocity going up, right? So it's difficult because now I've twisted my axes. Okay, believe it or not, going through the struggle of tilting your axes like that is, believe it or not, it's actually easier. because you have less things that you don't have to do. What that would effectively mean is that you have n and you have sines and cosines and all that stuff, and then you have to square that and then blah 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 blah. There's much less round off error, and believe it or not, there's actually a lot less moving. There's a lot less moving things around when we tilt our axes like that. I can assure you, having gone through the struggle of having to do things this way myself, I think it's like a third of the computational power to just tilt it and go like that. Cool. Sweet. That was a good question. Are there any other questions? Did that answer your question, by the way?
Yeah.
Okay, sweet. I don't want to feel like I'm brushing it off. Anything else? Nothing? Okay. With I kind of teased this a little bit. With the 15 minutes I have left, okay, I am going to ask the question, okay, is because what good is a science class if we don't get to walk away and say, I can put this stuff to good use, okay? Similar example, I still have my couch, okay? And in option number 1, I'm gonna, okay, in option number 1, okay, I'm still moving at a constant speed. Okay, I'm dragging my couch along the floor. Okay, but in option number 1, okay, I'm going to say theta is the same in both ways. Okay. Option number 1, I am pushing down like this. Okay, I'm pushing down on my box. Okay, and then option number 2 is I'm pulling, like I have a backpack strap or something, like I'm pulling a sled. Okay. Yeah, I'm pulling a sled. Friction is going to be opposing me. Okay. Friction is going to be opposing me either way. It opposes me in the direction of the frictional coefficient is going to be the same. Okay. In which case does the magnitude of my force, in which case is that going to be greater or less, okay? In order to get that to move at the same speed, which way do I have to work harder, basically is what I'm asking. Okay, in the case where I'm pushing it, or in the case where I'm pulling it, okay? How many of us have had to move furniture before? We've probably all had to move heavy objects around at some point in our lives, right? Have any of us ever noticed that when you push something, okay, it feels different from when you pull it, okay? Any ideas as to why?
Because there's less friction going downwards in the ground compared to upwards.
Yeah, so check this out. We have force is a vector, okay? So in both cases, my x component is exactly the same, okay? But watch what happens to my y component, okay? In the pulling example, where I'm pulling that with a cable, I have a y component that's pointing up, okay? And in the case of pushing it, I have a y component that's going down. Okay. Now remember, the normal force is pushing back to you however much force is being applied to the ground. Okay? So in the pushing example, in the y direction, okay, so that's still mg, nothing's changed there. My normal force is still going up. Okay, in the y direction, okay, so for the push direction, the sum of all my forces in the y direction, that's the normal force. In this case, it's going to be minus my force, and that'll be sine theta. I'll spoil that for you. Okay, and then it'll be minus mg equals 0. My couch isn't moving up or down. And in the pulling example, that's supposed to be pull. The sum of all my forces in the y direction. Now I still have n, but I have the plus F plus F sine theta minus mg, okay? So what does that tell me? My normal force, in this case, is going to be F sine theta, that's not 8, theta plus mg. And in this case, my normal force is mg minus F sine theta. So if my, in this case, which one has a greater normal force? When is the ground pushing back harder? When you're pushing or when you're pulling the couch? When you're pushing the couch. So what does that mean about who put that there? If my frictional force is proportional to my normal force, what does that mean? What does that mean for my, when is friction going to be greater, when you're pushing or when you're pulling? Friction is going to be greater when you're pushing. Okay, so if you want to make your life easier, what should you do if you want to make your life easier? Okay, when you're moving, do you want to pull your furniture at an angle or do you want to push it down at an angle?
Pull your furniture.
You want to pull your furniture, right? This would be easier. Or I guess a better way of saying it is not necessarily inherently pushing or pulling, but you want to have forces that have a positive y component that go up from the ground. So you could get down and push like that, but I feel like that's going to make your life harder. Just pull your stuff, okay? Did that kind of answer your question from earlier? Sweet. Okay. I don't think I can do anything meaningful in the next 10 minutes. Are there any questions about anything we talked about today? Okay, sweet. My plan is tomorrow, we're going to put this to use. I'll do an example for you tomorrow, okay? We will add together vectors, and that'll be our lab tomorrow. My goal on Wednesday is basically to do maybe 1 or 2 more examples of this, and then the world's fastest review. And then Monday, campus is closed. Okay, we have a holiday, so sleep in, rest up, maybe use some extra time to study that you have, and then we'll be right back here on Tuesday of next week for our first exam. Okay, I'll see you guys here tomorrow. Yeah.
What about a reference sheet? All the
You got this.
with all the